Hello everyone, welcome to part 3 of video number 4. In video number 4 we are trying to calibrate a model from a mountainous region in Argentina. In the first part of this video, what we did is we built the SWAT-CUP model of the region and we looked at different components of SWAT-CUP. Then we got an initial run of the model before any calibration, and we visualized the original simulation that looked something like the picture below. The blue line is the observed discharge, and the red line is the simulated discharge of the initial model. It did not look very good, but by looking at the observed discharge, it's very regular, as you see. It seems like every spring you have a peak that is indicative of some snow melt. So we went and had a look at the region, and sure enough, in the region, it's a mountainous region. It has a lot of snow on the mountains, and our watershed is just at the headwater of the snowmelt. Our climate station, we only had one climate station at the corner of the watershed, which clearly does not represent the climate of the high mountains here. So the least we could do, as there were no more climate data, the least we could do is add elevation band. And elevation band, as you know, as you go up by about a kilometer, your temperature decreases by about 6 degrees, and your rainfall can increase quite a bit, even up to 1,000 millimeters and so. So, in video number 2, in part 2 of video number 4, here's what we did. We reviewed SWAT-CUP input files. We discussed what R, V, and A parameter qualifiers mean. We discussed some identifiability issue of parameters. We added elevation band, and we fitted and fixed T-labs and P-labs. So here was the result. Here you see the 95 PPU in green, and your measured and the best simulation model runs. So it seems like we have made quite a bit of improvement to the model by adding elevation band. And here is what the final results look like. This is our initial run, and this is the run after fitting T-labs and P-labs and then fixing their values to the best simulation. So you see the NISA cliff went from minus 1.3 to 5.3, which is a major improvement in the model. So currently that's where we are. Let me just go down here. This is the history of what we did. We initially chose a dummy parameter and looked at the initial model, and then we fitted the P-labs and T-labs, and then we again looked at the best of what we had so far. And in our iteration history, we saved the iteration history, and here again you can see that we initially ran the original model, and then we added elevation band, and then we fixed the parameters of elevation band to the best the values. Now, before I go on, when we did the fitted these two parameters, I forgot to do sensitivity analysis at that stage. So I would like to do some sensitivity analysis so I can go back to this saved iteration. And here is the 95 PPU of that iteration. Here is the dotted plots. We did look at the dotted plots, and you could see that this is P-labs has a more random distribution, and T-labs had a trend that indicated clearly as T-labs value increased, the NISOT cliff value decreased. So by just looking at this, I can deduce that my T-labs is much more sensitive than P-labs. Now I can confirm that by doing a global sensitivity analysis. And here is a visual graph. I prefer the grid. Here we show the result of sensitivity analysis with two parameters, T-stat and p-value. The larger the T-stat in absolute value, the more sensitive the parameter, and the smaller the p-value, the more meaningful is sensitivity of that parameter. So in this case, you see that T-labs has a very large T-stat and a very small p-value. You would like this p-value to be actually 0, if possible. And the reason is not 0 is that we made only 64 simulations. So if we had made a larger number of simulations, you would get this value to be equal to 0. But anyhow, this shows that my T-labs is much more sensitive than P-labs. So let me go back now and let me close some of these, and I would like now to add the snow parameters. So the next logical thing would be to edit my snow parameters, try to fit my snow parameters. So I go down here in the examples and I grab these nicely set of parameters which are put here, and I copy it here. Let me get rid of this line. So these are my 5 snow parameters. Now notice that these reside in the basin. We only have one basin file, right? And so these parameters therefore apply to the entire region. Now you probably know that the snow parameters could be made spatial. That means you can fit snow parameters for every sub-basin individually. Sometimes one corner of the watershed, maybe you have mountains, and another corner you have also mountains, and they may be different. So you may want to fit your snow parameters as a spatial parameter. And you probably know that to do that, you can, you see, when you are in ARC SWAT, when you are editing your sub-basin parameters, there is an option here that says use sub-basin snow parameters. So if you check this, then you will get a whole bunch of .SNO parameters for every sub-basin. So you could practically fit the sub-basin snow parameters for every sub-basin. But in this case, we are not going to do that for this small sub-basin. So I have here a range from -10 to 10, but usually they change from -5 to 5, these two parameters. And then the next two parameters also change from 0 to 5. So I'm just going to make this narrower, the range, so we can just do one simulation, one iteration. And so I edited this previously, so I have 5 parameters, and I would like to do 128 runs, simulations. So here again, I do 1 to 128, even though in this program, parallel processing, it doesn't matter if I fix this or not. Parallel processing does not look at this. But in SWAT Plus it does. So that's why it's a good practice to always set these two together, these two files, parinf and the SWAT edit file. So after fixing this, I save everything, and then I make sure the parallel processing is on, which it is, and then I do a run, which will take a few minutes, and run. Okay, that's my parallel processing working. It copies the program to 8 processor, and now each processor does about 16 simulations. All right, good. So our program ran, and I recorded a few things to show you. One is when I was doing the parallel processing, I noted here the time that it took to make the 128 simulations. It was 9 minutes and 12 seconds. And then I ran the program without parallel processing and just a single process, and it took 17 minutes and 2 seconds. So about twice as much time it took to run it without parallel processing. Now this is a small project, and we did a small number of runs. So when you have a larger project and SWAT takes longer to run, the difference could be really a matter of days and not minutes. The reason is that when I'm doing parallel processing, I'm using 100% of my CPUs. So you see every CPU is running at the maximum, and when I don't use parallel processing, I'm only using 25% of my CPUs. This is the memory usage, that's the RAM. It is quite important that you also notice this. Sometimes when I open and close too many programs and I'm doing too many things, this can go up to here and occupy most of my RAM with remains of previous projects and programs and so on. So it's important that every once in a while you restart your computer so that this can go down to its minimum value. Now let me go back to our project here, and so the run is finished. And also the reason I use the 128 simulations seems to be an odd number is because it's a factor of the number of CPUs. I have 8 CPUs, and I try to make this a factor of that. So this was 16 times 8. So every CPU did 16 simulations. Of course, it doesn't matter for parallel processing if I use 130. Still, it's okay, but it's better to use a factor of the number of CPUs that you have. So now let me run the post-processing and look at our results. The post-processing, as you notice, it's very quick. And let me look at the 95 PPU plot. So it's sort of similar. There are a little bit of changes. But I have to go to summary stat to see what difference has been done by running, by fitting snow parameters. And so this is telling me that 128 simulation, the best simulation number is number 90, and that's my SWAT-CUP value is 0.63. If you notice, the last run that we did, it was here, and my SWAT-CUP was 0.53. So I jumped from 0.53 to 0.63 after fitting the snow parameters. Not as severe improvement as the previous case, but still a significant improvement in my best simulation. I have SWAT-CUP of 0.63 now. So let me go down here and look at the dotted plot. So the dotted plot gives you the result for every parameter. So here I can get an idea of the samples that have been taken, and also the significance of every parameter. As I said before, the more random the distribution, the less sensitive is that parameter. And if there is a trend, then that is a more significant parameter. So by looking at these dotted plots, I really cannot distinguish these parameters from one from the other. Again, here is the best parameter fits, the values, and here you have the best simulation and then the goal function. So that's the change. These are the 128 simulations here, and the parameters and the objective function value. And then the summary, the new parameter, so gives me a new range that I could, if I want to do another iteration. Now, the way to decide whether to do another iteration or not, this is one way, is that look at the range of my parameters. I went from -5 to 5, right? So if the best fit is very, very close to this parameter, that means I should probably extend this further down. And if it is very, very close to the upper limit, then I should extend it in the other direction. So that's one way I decide whether I should do another simulation, another iteration or not. In this case, this parameter could probably benefit from a smaller value. And if you look at the new parameters, you see that it has pushed this parameter further down, right? So if I wanted to make another iteration, my range would be to -9 instead of -5. But for this example, we'll just take this. And the next thing I want to show is that, well, first I'm going to do now a sensitivity analysis of this run and make sure I'm in the right place. Yeah. So if I do sensitivity analysis, global sensitivity analysis of my 5 parameters. So let me go to grid view. Again, I can sort this by, I can sort the t-stat values. So here you see the t-stat values for most of these parameters are very small. That means with the number of runs that I made, they are not very sensitive. The most sensitive one is this parameter here, but its p-value is rather large. So this is telling me that I did not do enough simulations to really identify which parameter is most sensitive. But anyhow, so that's the result of my sensitivity analysis. Another thing that I want to show you here, so let me just save this iteration. I save this iteration. This is my iteration number 2, and I'm just going to write here snow, so I know that here I fitted the snow parameters. Now I want to show you something that is important. Now our objective function here, we chose nice Sutcliffe, right? And you can see that here, objective function in my observed. I chose nice Sutcliffe as my objective function. Now, what would happen if I chose something else? So let's say, for example, if I chose r squared, right? Let me save this. Let me close everything and just open my observation. So if I choose r squared as my objective function, to see the result of that, all I have to do is run the post-processing, right? I have already made my runs, and so here I just do a post-processing. Takes a second to give me the results if the objective function is r squared. I can just go directly, let me look at the 95 PPU. let me bring out the previous 95 PPU. That was iteration 2 snow, and output and the single objective. So that is my previous 95 PPU with nice SWAT-CUP, and this is with R squared. So you see a little bit of difference, right, in the simulations of the best parameter. So let me look at the summary stat. The summary stat of my current run with R squared. So here is goal type R squared. My nice SWAT-CUP is 0.56. My R squared is 0.8. Now previously, when I had nice SWAT-CUP as my goal function, nice SWAT-CUP was 0.63. Now it's 0.56. R square is with 0.82, and when I chose nice SWAT-CUP, it was 0.78. So it's clearly, if I have nice SWAT-CUP, I get a better nice SWAT-CUP value. If I have R squared as my objective function, I get a better R squared value. This is clear. Now, let me go to the best parameters. So the best parameters are these 5. I can also go, let me just grab these as my best parameters. I'm just going to copy this. Let me bring it into my PowerPoint, and I'll save it in here, for example. So this is my parameters, or best parameters, when I have R squared, right? So let me just write R squared here. And then if I have nice SWAT-CUP, so that would be down here. My best parameters when I have nice SWAT-CUP, right? Nice SWAT-CUP as the objective function. Let me also bring that here, and say nice SWAT-CUP. So now you see the difference in the parameters. Now the simulations were more or less similar, right? R squared 0.82, 0.78 or so. It was more or less similar, but look at the difference in my parameters. Now, if I go back and I choose something else, let me close again some of these and go to my observation file, and instead of R squared, let me choose, I don't know, let's say P bias, right? It's most commonly people use these. So I use number 8 as my objective function. I save this, and all I have to do, again, run the post-processing, and in a second I get the results of nice SWAT-CUP, of best parameters. Let me again grab the best parameters for P-biased. I'm up here. Best parameters for P-biased. The best parameters are these. So let me again copy this and bring it here so we can compare them. And this one is P-bias. Now, what's happening here is that as I change my objective function, my parameters can change quite a bit, right? They can change quite a bit. Now, these are the snow parameters. Some more important parameters like CN2. CN2 determines how much runoff I get compared to how much infiltration I get. That's where the rainfall is divided into runoff and infiltration. And sometimes if CN2 is very high, then my watershed is runoff dominated. If CN2 is very low, then it's infiltration dominated. And I can have very different parameters. So if I choose R squared, it tells me my watershed is runoff dominated. If I choose nice Sutcliffe or P-bias, it can tell me that it is infiltration dominated. So the difference could be really very large, right? You know that the parameters represent processes in the watershed. So I could, by changing my objective function, I could have different watersheds. So what does that really mean? Well, it means that my calibration result is conditional to my choice of objective function. So my calibration results are always conditional, not only to the choice of objective functions, but to many things, many of the assumptions in my project. But this is a critical one, because if I change objective functions, I can get good calibration results in any case. But then the characteristic of my watershed can change based on my choice of objective function. So this is really a major problem, and we try to address this in other papers, this issue. So what do? So conditionality is always not good. You should always, your results be unconditional. That means it doesn't matter what happened, your results are correct. So that's why we introduced multi-objective, right, in option in the new program in the SWAT-CUP Premium. You can have multi-objective. That means you can build an objective function made of all these different choices of objective functions that we normally make, and by that my result would be unconditional. That means it doesn't really matter, because to go from conditional to unconditional, you have to integrate over all those conditionalities, right? So if I integrate, or if I add all of these objective functions, all of these goodness of fit measures, let's say goodness of fit measures, if I add all of these and make an objective function from all these, then my result would be unconditional with respect to the objective function. Okay, so let me bring another point to your attention, and that is if you go to the goal file here, and you see here, these are different combination of our parameters of the 128 simulations we make, and this is the objective function value. My objective function here is nice Sutcliffe. Now you notice that quite a few simulations have really poor objective function value, or even negative nice Sutcliffe values. So I maybe not want to look at those, and I just want to look at all the simulations where nice Sutcliffe is positive, or nice Sutcliffe is larger than 0.5 or 0.7 or so on. So in other words, I want to put a constraint on my objective functions. I can do that by choosing the single behavioral. Behavioral means you set a threshold, and the program only looks at the objective function values that are larger than that threshold, right? So we looked at the multi-objective. There is also multi-objective behavioral. So it would be nice to try different things and see their effect. We still have quite a long ways to go in calibration of a watershed model. So it's nice to be innovative and try different things and document what effect they make. Now, let me go back here. Now, at this point, I don't want to do any more iterations of the snow parameters. I just want to to fix their values at this point. So again, I go to my summary stat and I see that simulation number 90 gave me the best result. So I'm going to go back here as you saw before, and I put this to 90 and also the ending simulation to 90. I save this, or save all and close all. Now again, I go to calibration. I don't run pre-processing. I don't want to resample. I just make a run. So if I make a run, only simulation 90 is being run here. So what happened is all the best parameters were put into the SWAT files. Now I can check that. It's good always to check and see if this is being done correctly. So these were my best parameters. So I just go to my project here, open project folder, and I check in the basin file. We only have one basin file. So I look at my the 5 parameters. You see that they correspond very well to these parameters. So I did that. That's good. Now at this point, because I now fixed my snow parameters, I now fixed my elevation parameters. So what I want to do is to take them into my backup so that they are fixed and they are safe there. So I can sort this on type, and I can take all the sub parameters which contain my elevation information. They are over here. So I copy all the sub files, copy them, and in my backup, paste, and then I take my basin file, copy, and put it in my backup folder. So I know that up to now all my best parameters, the ones that I fixed, are in backup, so I'm fine there. So what next? The next thing is I would like to see my final result at this point. And again, as I did before, I'm just going to copy this, bring it here. This is just a dummy parameter that changes nothing. So I put this to 1 and here to 1. I go to this file, I make that 1 and 1. I make sure parallel processing is off. It is off here. So go home, and I save everything, close everything, and then I just make one run as I did before. See where I stand so far. Okay, and run post-processing and look at my 95 PPU. So this is my final result. My peaks are a little bit better than before, right? If I go to the best iteration of my after I did elevation band, right? So that's my iteration 1 best. So if I output 95 PPU, so that's what I had before calibrating for snow parameters, and this is what I have now after calibrating for my snow parameters. And I went from nice sod cliff of 0.53 here to I think it was 0.6 or 0.63 or so here. So I did make some improvements, but I couldn't make any improvements on the base flow here. And so what is going on? Now, going back to the region of my study, it's a mountainous region with high elevation, a lot of snow. You know that in mountains you have a lot of flow going, infiltrating through the cracks and micropores and so on. And then they show themselves up as springs, right? A spring is a common phenomenon in high mountain regions. So I can theorize that this is caused by springs that put out sort of a constant flow throughout the year. Now I'm going to put a outlet, I'm going to put a point source. So to account for springs, we can add a point source. That would be to account for a spring. So in my file, I didn't put a point source before when I was creating the arc at the arc SWAT. It would be a good practice to put a point source in every subbasin. That is a very powerful thing to account for these kind of things like springs, for input from water treatment plants, sometimes irrigation, and other things, other processes that either take water or put water at a point into the system. So I'm going to try this theory. I'm going to add a point source to my project, and I can do that very easily without going to arc SWAT. And I show you now how you can achieve that very simply. All right, so first I'm going to save this iteration, and I call it iteration 2, which is my snow and the best result that I got so far. And then to add the point source, I simply refer you to page 35 in the SWAT input-output documentation. Here you can see how you add a point source. And I will show you. Let me go to my project folder. You have to modify the fig file that has the structure of your routing. After the subbasin is finished, right, you can add a constant recharge, such as the one I'm showing here. So when the subbasins are finished, then you add a constant recharge. Oh, sorry. You add, I just want to copy this, you add a constant recharge line followed by a point source file line. So I just copy this and I bring it here. So I add a recharge constant. 11 is the code for a constant recharge, right, as shown here. Number 11 is the code for this constant recharge, and then 10 is just a unique number where it stores the information, and 1 is the number of file that follows, and we only have one file here. So then you write point source, and I put it in subbasin 17, which is one of the subbasins in the high in the mountain. I will show you that in a minute. And then that's it. And then I just have to make this file. So all I had to do was just add these 2 lines after the subbasin is finished, and then make these files. So let me save this fig file. And then I go back to my project and let me get the map so you can see. I get the map, and then we have already created the JSON data, and that is this GeoJSON data is in ArcSWAT GeoJSON. So let me get my subJSON and bring it here. So this was my watershed, and number 17 is just one of the upstream basins I just added here. So what I have to do now is actually nothing. I just have to run. No, I just have to make this this file. The file, you can get that file from either your previous projects. It's just or one of the SWAT examples. It's just a DAT file. It's a DAT file for the point source. I have it here. I created it before in the discharge. This is the file. That's how it looks like. You can get this from SWAT input examples, or you can simply create this in ArcSWAT and then edit it for your purpose. So I just copy this and I put it in my SWAT-CUP project here. So I have the file. And the number, this file, you can add constant water quality, water quantity. It's a long file, but everything is 0. I'm only interested in flow. And this number I got, initially I estimated by looking at, let me get my previous simulation in my output. 95 ppm. So this distance here, this difference, I am assuming that it comes from point source. So you just calculate this sort of average, this difference here, and then this is cubic meter per second. You convert it to cubic meter per month because we are doing monthly simulation, and that's that number. So let me go to this, right, this 8 or 8.5 or 8, that's that number. So I'm just, all I have to do is make a run, and create, and then post, then run it, and then post-processing. Okay, so I can have a look at my output. So that's what happened. I brought, it was from a big gap here. The gap was lowered quite a bit. Still, there are some areas that there is a gap, but it seems like in this year that began here, there was less snowfall or less rainfall, as you can see. Therefore, less maybe discharge. But so this is my final simulation and my final calibrated model. Now I could do many other things. I don't recommend that you try to get these exactly right and get these exactly right, because by doing that you'll be conditioning your parameters more and more and more on the calibration data that you have, right? And then if you do that, if you condition too much, try to get everything right, which is not a good idea, because there are probably other things that we are not accounting for. Then your validation will not be very good. If you condition your calibration too much on your calibration data set, your validation is not going to be good. So it's better to do what I call a light calibration always. If I get a paper where the NISOT cliff of discharge is 0.9 or even worse, I mean sediment, I see people report NISOT cliff of 0.9 I mean, I would really immediately reject that paper because I have done enough models, runs from different areas in the world to know that there is no way you can get sediment with a nice surf cliff of 0.9. It's just impossible because for the simple reason that what we measure, it's not what SWAT gives you. What SWAT gives you, it's 99% of the time not what you're measuring. And so there is no way you can get such a perfect fit. So just do a light simulation, and then hopefully you will get a better validation, and that's all you report. Don't play too much with your data. That's my suggestion. In this case, I don't have validation data. I had 6 years of data. I used it all to show you how the calibration process would go. I could have used 4 years of data for calibration and 2 years for validation. Maybe I do that in another video just to show what is the difference. What is the difference if I use all my data for calibration or use half of it for calibration, half for validation? What would be the difference in parameters that I obtained, let's say? And what does that mean? For this example, I have daily data. So I have daily data for 6 years, which is quite a bit of data. I could also run my model now using daily data. I try to calibrate the daily data, and then I could compare the parameters of a daily calibration with a monthly calibration. And you know, these parameters represent processes. So does processes, you know, when you calibrate, does that depend too much on your time scale? You know, if your time scale changes, suddenly your processes change, and you know, you could explore all of these. You know, what are the sensitive parameters, daily and monthly, and what do they mean? You know, and I suggest that instead of playing with data to get a perfect fit, which is not a good idea, you should try to deepen your analysis. I mean, the journals, most journals are tired of publishing SWOT applications, right? You get some data, you calibrate your model for a region, you build your model, you calibrate it, and maybe some of you, at most, you do climate change analysis or so on. So that's too many of these papers have been published. So I suggest that you explore, you know, more and try to deepen your analysis between, like what I said, the difference between monthly and daily calibration versus validation. And then you could do a single objective, the things I have put here in the program, single objective, multiple objective, behavioral simulation, and what do they mean for the final model that we get? And now with that model, we're going to do management, different management practices and optimize management practices. You know, so you can build many different good models. Which ones are you going to use? And what is the difference? I mean, we have done some papers looking at these issues, and I gave you a list of the publication before. I can provide you a list of publication again. So to explore more, to deepen more your analysis instead of trying to play with your data to get a perfect fit. Models are not perfect, you know. Don't try to get all the peaks, all the base flow. That is not, it is not right. I mean, it is not possible, and it's not right either. You end up massaging your data and so on. Don't do that. Just try to deepen your analysis instead of playing with data. So I'm going to end this video here, and I will have more examples that I will show you in future videos. Here we did not really calibrate. We didn't touch any of the SWOT parameters, right? We only tried to improve the model by putting elevation band, by putting snow melt, and by putting point source. So we didn't play with CN2, any of the soil parameters and so on. Maybe you could do that. I mean, at this point, you could take some of the general flow parameters, groundwater parameters, and so on, and make one run of plus and minus 20% deviation in your parameters, and slightly to see if you can get a better fit. But I doubted if you can get a much better fit, even if you play with parameters. But anyhow, that's something that you could do at the end. Just get general flow parameters and make one iteration, and to just adjust them slightly to the situation that we have. Okay, so in the next video, I will show you more projects. Thank you for watching.